what we've learned about so far is that the old system of doing electron configurations is not going to do what we need it to for this year. The periodic trends that we're going to have to explain, the oxidation states and other physical properties we're going to have to explain about the transition metals cannot be described using the old 288 system. So what we've got now is what's called the SPDF notation, and that's just about the different types of orbitals. So we've got S orbitals, which can take a maximum of 2 electrons, okay? Then after they're filled, we start filling the p orbital, which can take, there's 3 suborbitals, and each of them takes 2 as well, because electrons are most stable in pairs, so it can take 6. D, which has got 5 suborbitals, so it can take 10. And this is the orbital that gives the transition metals their properties. And then we've got the F block, which is down the bottom of the periodic table that we're not going to worry about this year. And probably you won't until stage 2 university if you do chemistry there. Stage 2 uni. So this is called SPDF notation. It is the notation expected of you now. So from now on we have to use this. However, you can summarise it using the old system, the 288 and so on, if it makes it easy for describing, for example, atomic radius. Okay, so we'll get to that later on. So what does it look like? Well, just like the old system, you start at the electrons closest to the nucleus, and this is what we call the first energy level. So if I was to look at phosphorus, for example, we see on the periodic table that phosphorus is number 15. Okay, so it's number 15. I'm not going to worry about its atomic mass because that's in the nucleus, and we'll leave that for physics. Okay, the fact of the matter is this means it's got 15 protons in the nucleus, which means it has 15 electrons orbiting it somehow in its electron shells or in its electron cloud. This is what we probably should really call it. So I've got to find a place for 15 electrons. Under my old system I would have said 2, well that hasn't got to 15, 8, well that's got to 10, and then 5. And that would have explained why it's got a valency of 3, because it's 3 away from being full. This explains why it becomes a 3- ion, because it has to take 3 to get full, and it won't lose 5. Okay, 5's too many. However, when we learn about phosphorus and we do Lewis structures with them later this year, we'll see that actually because of this it can make 5 covalent bonds, so that you can actually use those 5 for bonding. We'll get to that later on. So that's the old system that's okay but not good enough anymore. These are the electrons in the first energy level, second and third. So now I'm going to show you how you do it using the SPDF. Now the first energy level can only take 2 electrons. So that would suggest out of those numbers there, it would have to be an S orbital, because they can take 2. Whereas P's got 6, D's have got 10s, so that doesn't work for an orbital that, for an energy level that can only take 2. So if I was to do phosphorus properly now, then I'd say 1 for the energy level, S for the orbit type or orbital type, and then 2 as a superscript to tell me the number of electrons in there. Then I'm on my second energy level, so I have 2. I have to fill the S orbital first. So I do 2s2. I'm now up to 4 electrons out of my 15. I now need another orbital, so it must be the P. It's a 2 again, because it's still on the second energy level. I'm trying to get these 8 in total. The P orbital is filled. 6 plus 2 is 8, which is what I see there. Okay. I've got 5 electrons left, so surely I could just go 3p5. Done. That would make sense, wouldn't it? Because that can take up to 6, so I could just do that. No, I can't. I've got to fill my S orbital first. Okay. So I go 3s2. I've still got 3 electrons left. 3p3. Now, phosphorus is actually a particularly stable electron configuration, even though it's not full. And the reason is that this orbital, this p orbital, is half filled. All of the electrons, if we were to do a little diagram, this would be shown as an up arrow, up arrow, up arrow for the 3p orbital. They're all said to be spinning the same way. It's what we call maximum spin. So it's actually quite a stable arrangement. So although phosphorus as a compound, actually, as a molecule, is actually quite unstable, you can rub it and it catches fire, matches. As an atom, it's actually relatively stable. Okay, and its properties you'll see later are due to the fact that full energy level, full orbital, and a half-filled orbital, because half-filled orbitals are quite stable. This is a thing called Hund's rule. And it's a rule, not a law. So the difference between a law and a rule is quite important. A rule is something you can use, like drop and swap. It's something to help you remember something. It's not a law. A law is something like the law of gravity. Okay? Yeah, it is. There's a fundamental value for gravity. Okay? So laws don't get broken depending on the system they're in. So the law of gravity on this planet has got a value to go with it that doesn't get broken. A rule can be broken. So it's not always true. However, it can be used to explain things, and that's what you're going to do next week, is use it to explain some properties. The best way to show you where this becomes important is if I look at the electron configuration of chromium. And in this I'm also going to conveniently talk about the shorthand way to write electron configurations when they're probably from 10 and higher, so from neon and up, because there's a shorthand way to do it. Rather than writing all of this first, I can actually abbreviate it. So if I had chromium, and chromium is number 24, I need to have 24 electrons. This is where the 288 system falls down completely, because actually it doesn't work that way. So chromium would have 1s2, 2s2, 2p6, because I haven't got to 24 yet, 3s2, it would actually have 3p6 as well, because now I've only got to 18. 2 plus 2 plus 6 plus 2 plus 6 is 18. So I can actually ignore the first 18 electrons by doing this. Argon in square brackets means the electron configuration of argon, and then I will fill in the rest of it after that. It prevents me making a silly mistake. This means the same as 1s2, 2s2, 2p6, 3s2, 3p6. And writing all that out, you can imagine in an exam condition making a silly mistake, can't you? Making one of the numbers a 4, or making just a small mistake that you get nailed for. So we do that instead to avoid a silly mistake, costing us any marks. It means the same thing, so we're allowed to do it. By the way, if you're asked to give the electron configuration of argon in a test, go to the effort to write it all out. Okay? But you can't just go argon in square brackets. However, this is the cool thing. If you're asked for the electron configuration of, say, the potassium ion, which is 18 electrons, you can do that on its own, and that's allowed. Okay? So, some little tricks of the trade, as it were. Okay, so chromium, I've got 18 electrons. This is what I do when I'm doing this in an exam situation, so I don't forget. I put a little 18 underneath it. I'm going to cross it out at the very end. It's just to keep a tally in my head, so I don't lose count. I need to put another 6 electrons in there. Now the rules were, that we talked about yesterday, the next orbital we fill is the 4s orbital. Okay? Even though I'm going to get more electrons in the third energy level, I put my 4s electrons in. And that can take 2. Now there's only 4 left. So I now drop down to the third energy level again to start filling my 3d orbital. And that would allow for 4. I'm going to draw these out and show you why there's a wee problem here. That's my 4s. 2 electrons in the 4s orbital, spinning opposite ways so that they don't interfere with each other too much. And then I've got 1, 2, 3, 4 in the 5 possible spots for, or orbits, or suborbitals for D. This is not overly stable. Okay, this is not overly stable. What would be more stable is if this one had an electron in it as well, because then it would create maximum spin. It would satisfy Hund's rule. Well, conveniently, this can happen. This electron here can drop down into the third energy level, and it will be spinning the same way as all of these other ones. So now I've got the 4s and the 3d both satisfying Hund's rule. They both have maximum spin. This is a stable arrangement for the electron configuration of this atom. It means that I've got this wrong. I need to change it. I've now only got one electron in 4s, and I've now got 5 in 3d. Now the other the other fourth period, so the fourth row down, the other fourth period element that does this is copper. And I won't put that one on the board. I'll let you ever think about how that might use Hund's rule to become more stable. So the other really stable thing that can happen is you can have a full orbital, which is what we're doing here, filling the orbitals before we filled another one. So that's also allowed. Just a quick comment. This only happens once you get to element number 20. Before element 20, you just have to fill them like you did in year 12 and year 11. Okay? And that's why we taught you the simple model for the first 20 elements, this 2, 8, 5, and so on. Okay, so don't try to make Hund's rule work by moving things from a 2p orbital into a 2s orbital into a 2p, that sort of thing. That won't work. Okay. So, electron configurations using the SPDF notation. Rather than going 2, 8, 5, we have to break it down into 1s2, 2s2, etc. If you've got to beyond argon on the periodic table, so number 19 up, you can abbreviate it by having argon in square brackets and then breaking it down. If something has maximum spin, all of the suborbitals in its orbital half filled, we call this a stable arrangement. We call it maximum spin, which I'll write on the board. And this obeys a thing called Hund's rule. Okay, that this would be a favourable electron configuration.